And that's why we've invited Mr. Ravi Mehta from Silab Tech right here. Take it away.
Hi. Yeah. Hi, everyone. So I'll be talking about JESD 204B, which is a standard for communication with high-speed ADCs and DACs. So what is JESD 204B? It's a JTAG standard. It's a serial interface for communication with data converters, ADCs and DACs. And it's not a new standard. The last revision was released more than 2 years ago, more than 3 years ago in Jan 2012. So this is basically a summary of how the interconnect looks like. You have a bunch of connectors talking to an FPGA or an ASIC, and they are connected by several parallel serial interface links. And the latest version of the standard supports data rates from 312 Mbps to 12.5 Gbps per lane. And so the aggregated bandwidth can go well over 100 Gbps. And the electrical interface is based on the OIF CEI 11G short reach standard. So in the past, the interfaces with data converters used to be using IOs or even LVDS IOs. So what are the advantages of moving to JESD 204B? So it allows use of higher speed and higher resolution converters because the interface supports very large bandwidths, so you can move lots of data from the converter or to the converter. And because it works on SerDes technology, it uses fewer pins. There's lower power consumption per bit. And there's this feature called deterministic latency, which basically leads to synchronizing multiple converters and making them operate together. And I'll cover this part where there's a wide adoption of this interface by ADC and DAC vendors and also FPGA vendors. So here's one example of from one of our customers where they use 8 channels of our SerDes IP, which works at 12.5 Gbps per channel. So that's a raw bandwidth of 100 Gbps with just 16 pins for the 8 channels. And that consumes less than 475 milliwatts of power total. And compare that with LVDS, where even with, let's say, a 1 Gbps per lane of LVDS IO, you need 200 pins, and the power consumption would easily exceed almost 2.7 watts. So that's the level of difference it makes by going to the SerDes technology. So yeah, this is just a small list of some key products which support the JESD 204B standard on the ADC and DAC front. So these are some example products, and you can see how fast and how many channels of JESD 204B some of these products support. And these are really high resolution, high speed converters. And this interface is also supported, let's say, by Xilinx FPGA, where they provide the JSD 204B core IP for use in their FPGAs. So this is a picture of the Silab Tech JSD 204B IP. What we call this is a JSD 204B subsystem. So this basically includes the JSD 204B MAC or the controller and a bunch of SerDes channels. And they are hooked up together with some supporting logic. There are registers which communicate to the SoC using an APB interface. And these registers are used to configure the MAC or the SerDes. And then there is the wake up logic for the SerDes IPs to power them up and sequence the power up of the IPs. So what we deliver is a completely integrated and verified subsystem with the MAC and the SerDes integrated. So here are some highlights of the IP. So we have this IP prone in multiple process nodes. There is a very big advantage on power and area, especially on power, and we can share the power numbers with you. what we provide is a fully integrated and verified solution. We have not just the SerDes, we have the SerDes and controller, and we integrate and verify them together. So that completely integrated solution is provided. And the integrated solution is verified with a third-party VIP. And we also have support for customization, especially on the controller side where there is an interface with the SoC. And what we provide with this integrated IP is a validation platform for prototyping using an FPGA. So these are some highlights of the SerDes IP itself, which is a part of the subsystem. The SerDes supports single or multiple lanes, and it covers the entire range of data rates supported by JESD 204B. And this SerDes is designed to talk to different types of connected devices in different channels. So the transmit part of the SerDes is configured to output a very wide range of swing, and this goes beyond the range dictated by the standard to work with devices which are not fully compatible, but you need to still output a higher swing to make it work. It also has programmable equalization on the TX path. It has adaptive equalization on the receive path, so it can really provide a robust solution in various channels with various devices. And it includes a very low jitter PLL inside the IP itself. So yeah, on the SerDes side, these are some of the silicon results. We have the IP on silicon in TSMC 28 HPM and GlobalFoundries 28 SLP. We have it on silicon in few other nodes. So these are some of the example snapshots. So these are the silicon results for the TX. This is the far end eye diagram at the end of a short reach channel. And yeah, this is the eye diagram at 12.5 Gbps. This is at 6.25 Gbps. And on the right here are the CDR test results at 12.5 Gbps. So this is the standard specified mask, and you're supposed to be always above it for jitter tolerance. So on the controller side, the controller supports both subclass 0 and subclass 1. So subclass 1 on JESD 204B is basically a feature where multiple sets of converters can all be synchronized together to provide what they call as deterministic latency, where the output of an ADC till the point it reaches the processor, that the delay of that is deterministic and it is known. And the controller IP that we have, it can do a programmable level of programming of the logical to physical lane. So any logical channel can be mapped to any of the physical SerDes channels. So this is something that proves to be very useful when you have in your application board, you have some problems with the PCB where you cannot achieve the same ordering of lanes. On the interface to SoC, we have a very simple stream interface with programmable width to get the ADC or DAC streaming data. For the DFT, we have a IEEE 1500 interface, and this is something which can be directly plugged into SoC IEEE 1500 TAM or JTAG TAM. The IP supports various features, and some of them are error reporting using interrupts, and there are various registers to mask or unmask some interrupts. On the DFT and test side, again, there are lots of standard digital DFT features for Stacat and TFT scan. And then there is a boundary scan for testing the SoC digital also. So this is the validation platform for our JESD 204B controller. So on the left here is the case A is showing how we validate our TX controller. So we have our TX controller on an FPGA, and we also have on the other side we have a Xilinx JSD 204B controller. And what we do is we use the GTX macros on the FPGA, and we pass the outputs to a loopback board and bring it back to the Xilinx JSD 204B controller. And this is how we test the complete data path and the interoperability of our controller with the Xilinx controller. And in the same way, we also test our receive controller. So we put the receive controller, and the Xilinx TX controller drives the data, and then there is a data generator and checker which validates the path. So this is the picture of the next level of validation, where the controller is on the FPGA and our SerDes is on the test chip. So the previous example was where the SerDes was on the FPGA itself. It was a GTX macro. So this one is the example where we have a test chip which contains the SerDes, and then it's on a daughter board which plugs into the Xilinx evaluation board. And we put the controller on the FPGA, and the SerDes is on the test chip, and then we do the same validation. So when you start working with JSD24B, you realize that the entire system design has several aspects which can be confusing, and it can lead to quite a lot of effort to resolve all the complexities. There are questions related to how many lanes, how many data, what data rate per lane. Then there are how to control the synchronization of the ADCs, the clock source, the clock structure of the SoC itself. So we provide consulting on the design of the entire system with the JSD204B. So this is one example where we worked with our customer, and this is what we propose to them, where we have our RX IP talking to several of ADI data converters, and we proposed the entire structure of this interconnect, and how they should decide the clock structure. We also provided the LVDS IOs and all of the associated logic that goes along with this. So these are just a few of the examples of what our customers are doing using our GSD204B IP. So we have customers building RF DAC and RF ADC in TSMC 28 HPM for a cellular base station application. Then there is a customer who is building a satellite receiver in Global Foundries 40 LP. This is where we are providing the SerDes and the controller. Then there is a customer building a LT data processing ASIC in TSMC 28 HPM. We have another customer who is building a radar ASIC in TSMC 40 G, and they are licensing the controller from us. So yeah, this is a summary of all the things I talked about. JESD204B is a standard for communicating with data converters, and it saves on pins, it saves on power. It allows you to use very high resolution converters. And Silab offers a completely integrated and verified solution for this. We have our SerDes, we have our controller, and we have integrated them together to provide one solution. And this is a very low area and power solution proven on silicon. And for evaluation, we provide FPGA validation platforms for the customers to build their prototypes. Yeah, that's it. Thank you.